This video gives some examples of simple algebra with logs. So in general terms, these videos are aimed at people who've just left school, just entering university, and in particular, engineering undergraduates. So far, we've given students a reminder of powers and indices, definitions and properties of exponential functions, and definitions and simple properties for logarithms. This video is going to look at using the properties of logarithms to solve some simple algebraic questions. Now, background before we start, logarithms have got some nice properties which are directly linked to the related properties for exponential functions. So for example, we saw that the log of a product is the sum of the logs, or the log of a quotient is the difference of the logs, and the log of a power is the power times the log of the original number. We also saw that the log of a simple exponential function is a straight line. So here's some questions for you. Simplify the following. So I've got log e of e to the power a all to the power n times e to the minus 2b. So the first thing I'm going to do is use the product rule. So I'm going to write this as log e of e to the a to the power n plus log e of e to the minus 2b. Now, what I can do next is I can look at this first one and I can use the power rule on that. So that gives me n log e of e to the a. And this next one I can do by inspection because it's just got an e in it, so by definition the answer is minus 2b. And then I can also see by inspection log e of e to the a is a, so I've got n a minus 2b. So we're done. So you see that first question looked quite messy, but actually was fairly straightforward. What about this next one? Log e of b to the minus 3 of a to the minus 2. So here I'm going to use the quotient rule. So I can write this is log e b to the minus 3 minus log e of a to the minus 2. Next, I can use the power rule. So this gives me minus 3 log e of b, and then minus 2 log e of a. And so now I can just rearrange the signs, and you see what you get left with: 2 log e of a minus 3 log e of b. And if you wanted to, you could use these numbers up here if they were given, and of course that gives 2a minus 3b. Next one then. Simplify the following. And this again, although it may not look like it, is just testing students' abilities with the rules of logs. So if I write down by inspection, or I use the product rule, then you can see what I'm doing here is adding logs together. So I can say equivalently, this is equal to log 10 of 23 times 6,000 over 4.6, because you can see the log of a product is the sum of the logs, the log of a quotient is the difference of the logs, so you can see that negative I must be dividing by the 4.6, a plus I must be multiplying by the 6,000. Now as soon as I've done that, it becomes straightforward. The 4.6 and the 23 clearly cancel to give me just a 5, so I get left with log 10 of 30,000, and I can write that as log 10 of 3 plus log 10 of 10 to the 4, and log 10 of 10 to the 4 is just 4, and so you've got log 10 of 3 plus 4. What about the next one? Again, it's just inviting you to use the standard rules of the log of a product and the log of a quotient. You can see I've got a minus here and a plus here. So I can write down that this simplifies to log 10 of 10 to the minus 4 times 7 squared, all divided by a third, Okay, now in fact in this particular case I could have left the 10 to the 4 out, because if you look at log 10 of 10 to the minus 4, I could have written that by inspection. So if I wanted to, I could start again. I could say in fact what I've got is minus 4 plus log 10 of 49 times 3. And indeed, that's as simple as you're going to get this. You can multiply the 49 and a 3, but that's rather a trivial point. What about this bottom one? You've got log e of e to the at. I can write down by inspection. That's at. The minus bt, there's nothing to do there. And then I've got minus 2 log e of 10 plus log e of 10 cubed. So this is going to give me log e of 10 cubed over 10 squared, because 2 log e 10 is log e of 10 squared, but there's a minus, so it goes in the denominator, so I get left with a minus bt plus log e of 10. What about this one? Now this one looks perhaps a bit messier, and you've got a combination of wanting to use the power rules and the product rule and the quotient rule, but if you just keep a clear head, you'll see it's relatively straightforward. So what I'm going to do is put everything in a single log, just using the product and the quotient rule. So log 10, 2 log 10 of 4 cubed gives me 4 to the power 6. Log 10 of 2,500, so I'm simply multiplying by 2,500. And now I've got a minus sign, so I'm going in the denominator, but also I've got a 0.5, which if I put the 0.5 in, it halves all the powers. So what I'm going to get is 2 squared over 9. And so what this gives me is log 10 of 4 to the 6 times 2.5 times 9 times 10 to the 3, all divided by 4. Now that's relatively straightforward to simplify. You may or may not see it straight away. I can cancel that 4, get rid of that 6 and make it a 5. I can then combine one of the 4's with the 2.5 to make another 10. So I'm going to end up with log 10 of 4 to the 4 times 9 times 10 to the 4, and that's going to give me log 10 of 4 to the 4 times 9, which I'm not going to bother multiplying, plus 4, because log 10 of 10 to the 4 is 4. Now there are other problems where the academic may expect you to be familiar with simple values like this. It always helps when you're doing logs to know what some of the values are off by heart. So common ones you'll come across: log 10 of 2 is about 0.3, log 10 of 3 is about 0.48, log 10 of 4 is about 0.6, log 10 of 5 is about 0.7. To be honest, if you know those 4, you can probably do anything that you're going to need. So an example here, if I wanted to know what was log 10 of root 2, then I could say, well, clearly root 2 equals 2 to the half, and therefore I can write it as 0.5 log 10 of 2. But you'll notice I know log 10 of 2, and therefore I can get log 10 of root 2 must be approximately 0.15. Another example for you. What happens if somebody asked you to find, you can see down here, log 10 of the 5th root of 6, and you might think, well, how on earth am I going to do that? But you'll see it's relatively straightforward, because the 5th root is the same as saying 0.2 log 10 of 6. So I've just taken the power outside. And now all I need today is, well, what's log 10 of 6? Well, log 10 of 6, I can write 6 equals 2 times 3. So log 10 of 6 is the same as log 10 of 2 plus log 10 of 3. And I've already got the 0.2 outside, but the log 10 of 2 I know it's 0.3. The log 10 of 3 I know it's 0.48. And so I've got 0.2 times 0.78. So what you see with some simple algebra, I can actually get the logs of some quite difficult numbers, and I don't need to be looking around saying, oh, where's my calculator, or whatever else. So here's some examples of how you can use simple estimation to estimate the log of some perhaps messy numbers. So I've said, right, we want to find 9,000, 32 and 60. So to get 9,000, I just write it as a product of numbers I know. So 3 times 3 times 10 cubed, because now if I do log 10 of 3 squared times 10 cubed, that's the same as 2 log 10 of 3 plus 3 log 10 of 10, which I can do by inspection because I know log 10 of 3 and I know log 10 of 10. Similarly, if I had 32, I say, well, I know that's just 2 to the 5, so I can now do 5 log 10 of 2, which is going to be 1.5, or approximate. It's not exact. That's good enough. And what about 60? I can say 60 can be written as 10 times 2 times 3. So therefore, log 10 of 60 is going to be 1, that's log 10 of 10, plus 0.3, that's log 10 of 2, plus 0.48, that's log 10 of 3. We can also do things the other way. If I said to you, log 10 of z is 3.3, what is z? Well, what you can do is you can say, let z equal a, b. And therefore, log 10 of z equals log 10 of a plus log 10 of b. And all I need to do now is make up the log of numbers that I know. So what I'm going to do is I'm going to let log 10 of a be 3 and log 10 of b be 0.3. And what that tells me is a has to be 1,000 and b has to be 2. So now you can see that z must be 2,000 because z is just a times b. What about this next one then? I've got log 10 of z is minus 1.3. So I use the same trick and I can write log 10 of z equals log 10 of a plus log 10 of b, and I'm going to make log 10 of a equal to minus 2 and log 10 of b equal to 0.7. And therefore, what a gives minus 2? Well, you know it's 0.01, or 10 to the minus 2. And what gives 0.7? Well, it's 5. And therefore, z must be 0.05. And the final one, down here at the bottom, log 10 of z equals 4.78. So I'm going to write this as 4.78 equals 4 plus 0.3 plus 0.48. So I'm just writing the logs straight down. So if I do the inverse logs, then the 4 corresponds to a 10 to the 4, the 3 corresponds to a 2, the 0.48 corresponds to a 3, and therefore my z must be 6 times 10 to the 4. So some conclusions. We've shown that the algebra of logarithms is straightforward if you simply remember and implement the rules. It's also useful to memorize the logs, and I've emphasized here for base 10, of a few key integers, as this will allow you to estimate the answers that you expect. And that's important because that gives you the ability to check for gross errors. Did I press the wrong number in the calculator? Did I do something silly?